Welcome back. We're taking a look at the direction angles and direction cosines. Um, and this is related to the whole business about angles and dot products. And you'll see us use the dot product here momentarily. Anyway, direction angles are a way of orienting yourself in three-dimensional space. You see, when you're in three dimensions, you don't have an x-axis in the same way that you do in two dimensions. Two dimensions, there's an x-axis, and that provides sort of the basis for whatever angle. If you want to say what direction that vector is pointing, you could always talk about it in terms of the angle it makes with the x-axis. But in three dimensions, you're dealing with three different axes. And so you don't have the luxury of using the x-axis in the same way that you did with two dimensions. And so what I have here is a picture. Well, I'm trying to make a picture. There we go. We have a picture here of, let's just get rid of, well, maybe I can't get rid of that stuff. Okay, so we have a picture of a vector that's pointing out into quadrant 1, and you'll notice that it doesn't make an angle. Well, it does make angles with the three axes, but the fact that it makes an angle of alpha with the x-axis doesn't tell you as much as you would information as you would have in two-dimensional space. And so in order to have some information about this vector, its direction, we're going to use what are called direction angles and direction cosines. So the angles themselves are the angles that the vector makes with the positive x, positive y, and positive z axes. Now these are pretty easy to compute. If your vector, let's just pretend that this is the vector, um, let's see, 2, 2, 1, just for the sake of argument. So let's just say that that's your vector. Well, oh, sorry about that. The alpha, the direction angle, alpha here, is just the angle between that vector and the positive x-axis. And so we could easily just use this, I equals 1, 0, 0, as the other vector and find the angle between these two, which is actually quite simple. The cosine of that angle, we know this is alpha now, is going to be the dot product of a and I. So it's 2 times 1 plus 2 times 0 plus 1 times 0, that's the dot product, over the magnitude of a. And I was clever about how I chose a. The magnitude of a happens to be 3, times the magnitude of I, which happens to be 1. So notice that this cosine is just 2 over 3. In general, the cosine of these angles, the cosine of beta, is also simple. It's just going to be this number over the magnitude of that vector. So, and then the cosine of gamma is this number over the magnitude. So here we have this formalized here that the cosine of alpha is just a1 if you think of a1, a2, a3 as being the components of the vector a. So it's a1 over the magnitude of a, and then the cosine of beta is a2 over the magnitude of a, and a3 over magnitude of a for cosine of gamma. So there's some interesting expressions that we get when we, for example, this is a little interesting tidbit that you get from the dot product and the cosines. And this is just another way of writing the vector a. So if you know these angles or the cosines, then you can determine, I guess, the direction that a is moving, that a is pointing. So these cosines provide you with a unit vector that points in the direction of a, and which will be useful later on. I guess here's the unit vector thing. So let's go ahead and find the direction angles for this vector. So just to remind you, what we're going to do, step one is to find the magnitude. So magnitude of A is the square root of 1 squared plus 2 squared plus 3 squared, which is the square root of 14. Then the next step is to write the cosines, these direction cosines. So cosine of alpha is 1, you're using the first component, over radical 14. Cosine of beta is 2 over radical 14, and the cosine of gamma is 3 over radical 14. Finally, we can use our calculators to compute the actual or approximate value of alpha, beta, and gamma. And I'm doing that right now. I'm going to use the inverse cosine of 1 divided by the square root of 14. And then I can just use the entry key. So this is in radians. So then beta is the inverse cosine of 2 over radical 14. Interesting. Radians. And then gamma is the inverse cosine of 3 over radical 14, 0.6405 radians. So this particular vector makes sense. It has the smallest angle when you compare it with the z-axis.